Kia ora team, welcome to Level 2 Chemistry 2022 Structuring Bonding. Let's get into it. Okay, so the first question, question 1, a good old Lewis diagram question. Let's read it. Refrigerants are compounds that are used for cooling, such as in air conditioning units and refrigerators. Some commonly used refrigerants are shown below in the table. Draw the Lewis diagram for the following molecules and name their shapes. What I like to do is I like to start off by drawing a table, and let's do that for the first molecule, NH3. So we've got a nitrogen and we've got 3 hydrogens. The first column of this table is going to be finding out the valence electrons in each of these atoms. So if we look at our periodic table in the resource sheet, nitrogen is in the 15th column. So because it's in group 15, we look at the second digit of 15, which is 5, so we know that there are 5 valence electrons for nitrogen. Hydrogen is in group 1, so it has 1 valence electron. The next column we're going to have to look at is going to be how much it needs to have a full outer shell. So according to the octet rule, you need 8 valence electrons to have a full outer shell. However, there are some exceptions that you need to be aware of. The exceptions that we have here are hydrogen, which only needs 2, beryllium, which needs 6, and boron, which needs 4. One way that I like to remember these exceptions is by saying a silly little sentence which goes something like this. A little bit cringe, feel free to come up with your own way to remember it, but hey, if it works, right? So I have to be 6 times better than B4. Okay, feel free to use that one. As I said before, come up with your own way to remember things, but yeah, go with what works for you. Anyways, so nitrogen is not one of these exceptions, and so it requires 3 more to have a full outer shell. It currently has 5, it needs 3 to have a full octet. Hydrogen is an exception, remember, as we can see here, it only needs 2. It currently has 1, so it needs 1 more to have a full valence shell. Okay, the next step that we have to do is we have to find the neediest atom. As we can see in our table, the neediest atom is nitrogen because it needs 3 electrons to have a full outer shell. So let's pop that in the center of our diagram. Hydrogens can go around the nitrogen like this. And the column over here, okay, is not only the needs, but it's also signifying the bonds formed, okay? So, as we can see here, nitrogen forms 3 bonds, and it has to form between the hydrogens because there's nothing else to form it with. And each hydrogen, as you can see in the needs column, has 1, so they each form 1 bond. Now the last step is going to be to make sure that each of these atoms are satisfied with enough electrons. So nitrogen, does it have 8 electrons around it? Does it have 8 electrons around it? Well, let's have a count. Remember, these bonds are worth 2 electrons. So I've got 1, 2, 3, 4, 5, 6. No, that is not enough. So we have to add lone pairs of electrons, which I'm just going to add over here. Okay, so now we have 8 electrons around nitrogen. Does hydrogen have its full outer shell of 2? Well, as I said before, this bond counts for 2 electrons, so this hydrogen has 2, this hydrogen has 2 electrons, and this hydrogen has 2 electrons, which it's sharing with nitrogen. Okay, moving on to carbon. As we go, we should get a little bit more speedy with these. So we've got COO, valence electrons around carbon is in group 14, so it's 4. Oxygen is in group 16, so it has 6 valence electrons. And then in the next column is how many does the atom need to have a full outer shell? Well, carbon currently has 4 electrons, so it needs 4 more to have a full octet. Oxygen has 6 electrons, so it needs 2 more to have a full outer shell, and same with this oxygen over here. So the next thing that we need to do is we need to find the neediest atom. The neediest atom, according to our table, is carbon. So we pop that in the middle, and then we pop the oxygens around it. Carbon shows to have 4 bonds forming, but there's only 2 atoms around it. So what are we going to do? Well, this is when we have to incorporate double bonds, okay? So the things that it's going to form double bonds between are the oxygens. So I'm going to pop some double bonds here, and that's the way carbon can form its 4 bonds as shown by the table. That also satisfies the needs of oxygen, which shows to form 2 bonds each, and that's perfect. The last thing that we need to do, of course, is to see if each atom has its 8 electrons around it. So let's count it up. Carbon, it's got 1, 2, 3, 4, 5, 6, 7, 8. Perfect. Carbon is happy. Oxygen, let's have a count. It's got 1, 2, 3, 4. Oh, we need to add more electron pairs around it. So I've got 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Beautiful. And that is how we draw the Lewis diagram for carbon dioxide. Okay, the last Lewis diagram that we have to deal with, okay, is N2. So again, let's draw a table for this. It's just got nitrogen and there's 2 of them. Valence electrons. Nitrogen is in group 15, so we know that it has 5 valence electrons. How much does it need to have a full outer shell? It needs 3 more to have that full octet. So which one's the neediest atom? Well, they're both the same atom, so we don't have to decide which one's going to go in the middle. We just simply draw them side by side. According to the needs column, it shows that each nitrogen has 3 bonds. So we're going to have to draw these bonds between these nitrogen atoms because these are the only things it could form bonds between. Okay, so does each nitrogen satisfy the octet rule? Let's have a count. 1, 2, 3, 4, 5, 6. Only 6 electrons are being shared between these nitrogen atoms, which means we will have to add some electron pairs. So we've got 6, 7, 8, and we have to do the same for the other nitrogen over here. Beautiful. Now, I have gone ahead and given you the names of the shapes. This is something that you have to revise, okay? The reason why NH3 is a trigonal pyramid is all because of the bonding and non-bonding pairs. So the number of non-bonding pairs to bonding pairs will determine the shape. So as we can see here, there are 3 bonding pairs and 1 non-bonding pair, which results in a trigonal pyramid shape. Carbon dioxide, even though I've drawn it bent, do not be fooled, okay? The linear shape is due to 2 bonding regions over here. This is counted as 1 bonding region, this is another bonding region, okay? Because there are no lone pairs, this makes it linear. Again, with N2 over here, there are there are only 2 atoms, which means that it has to be linear, okay? So, moving on to part B, we have chlorofluorocarbons. Okay, these molecules are used as refrigerants in the 1970s and 1980s. One example of trichlorofluoromethane, commonly referred to as Freon 11, is shown in the table below with another refrigerant. Okay, so what we have to do is we have to compare and contrast the shape and bond angles of Freon 11 with SO2. So the first thing that you should do for these types of shape type questions is you should first talk about the regions of negative charge. Then we talk about the VSEPR theory, which links into geometry, bond angle, and finally shape. So let's go through the template step by step and answer this compare and contrast question. I'm going to start off with Freon. So, talking about the regions of negative charge. Freon has 4 regions of negative charge around the central atom carbon, as you can see here. This is 1 region, 2nd, 3rd, 4th region. Now let's go into the VSEPR theory. These regions repel for maximum separation into a tetrahedral geometry with a bond angle of 109.5. So you can see here that I've linked the VSEPR theory with geometry and the bond angle all in one sentence, okay? Remember, the VSEPR theory is all about the fact that negative regions are going to repel for maximum separation because like charges repel, opposite charges attract, okay? So VSEPR theory is all about these like charges, which are negative, wanting to be as far away from each other as possible, okay? Finally, we are going to talk about the shape. Remember, shape and geometry are different. Geometry is based on the negative regions. Shape is based on the number of bonding pairs and non-bonding pairs. So finally, there are 4 bonding regions and 0 non-bonding regions, which gives Freon 11 a tetrahedral shape, which is the same as the geometry. Okay, because this is a compare and contrast question, it's important to use terminology such as in contrast or in comparison to. So I've written that here. So let's use the template up above to answer this question in the same way. So we're looking at SO2 now. Alright, so SO2 has 3 regions of negative charge around the central atom S. We can see that in the Lewis diagram that we've got 1 region, the 2nd region, and the 3rd region. Okay, they're like little negative islands around the central atom. So, SO2 has 3 regions of negative charge around the central atom S. These regions repel for maximum separation into a trigonal planar geometry with a bond angle of 120 degrees. SO2 has 2 bonded regions and 1 unbonded region around sulfur. Therefore, SO2 has an overall bent shape, okay? So that is a good comparison with Freon to show the difference. And again, do not be fooled by the Lewis diagram. This is not going to indicate the shape. It looks linear, but it's not. It's actually bent due to the regions of unbonded and bonded. So feel free to revise that if that's something you're not up to scratch with. Okay, moving on to the next question. Freon works as a refrigerant in a refrigerator by evaporating, as shown in the equation below. Draw a labeled diagram for the evaporation of Freon, showing reactants, products, and the change in enthalpy. What I love to do is I like to highlight the key points that we have to establish within our answer. So as we can see here, we have to show the reactants, we have to show the products, and we also have to show the change in enthalpy in our diagram. So how are we going to do this? Well, as we can see here in the question, and the information provided, we have a positive enthalpy value. So this signifies that this reaction is an endothermic reaction, okay? It's an endothermic reaction. What is an endothermic reaction? Well, an endothermic reaction is a reaction that absorbs heat. Okay, so this over here, these reactants are absorbing heat. Okay, so when heat is absorbed, okay, the reactants start off with low energy. When the heat is absorbed, there's going to be an increase of energy, which results in the products having a higher energy than the reactants. So let's draw this on our diagram. So we start off with the reactants down below, and then because it's an endothermic reaction, heat is being absorbed, which results in the products having a higher amount of heat energy or energy. So cool, we've done our diagram, but we're missing our labels. So we have to show the reactants. So let's label the reactants down here. Reactants. I like to be specific, so I'm going to write the actual reactant. Okay, then we've got the products. And then we have to label the change in enthalpy. So the change in enthalpy is going from the reactants to the products, okay? And this is the change in enthalpy, which is equal to positive 25.2 kilojoules per mole. All right, so that's our fully labeled diagram, okay, for Freon 11. Everything has been ticked off. Cool. Okay. By referring to both the change in enthalpy and the attractive forces between particles in Freon 11, explain how this process can be used to cool down a refrigerator. Okay, so there are a few things that we need to do. Let's break down the question together. So we have to talk about change in enthalpy. That's one thing. The attractive forces between the particles. And we also have to talk about the process. Okay, so there are a few things that we need to talk about here. Okay, so the process. What is the process? It's the evaporation process of Freon. So how does the evaporation process lead to refrigerators cooling down? Well, what's happening during the evaporation process? Let's talk about that. So when Freon 11 evaporates from a liquid to a gas, the intermolecular forces of attraction between Freon 11 molecules are broken. So I've talked about the process of evaporation, and I've talked about the attractive forces between the particles. So Freon is a molecule, and so the attractive forces would have to be the intermolecular forces between the molecules. Okay, so tick, tick. The next part I need to talk about is the enthalpy. So what have I written? So the enthalpy. This involves an endothermic process, okay? Enthalpy is referring to either an exothermic or endothermic process. So in this case, this involves an endothermic process where heat energy from the surroundings is absorbed to break these intermolecular forces of attraction, okay? So now that I've talked about the enthalpy, I have to link back to the context of the question. So as the link, I've written, as heat energy is absorbed from the surroundings, the temperature of the refrigerator decreases as Freon 11 evaporates. So I've ticked every part of the question. This is something I recommend doing, highlighting the key points and making sure you're knuckling down on each of them. All right, heading into question 2 of this exam, Freon 11 is produced in the lab by the reaction of carbon tetrachloride with hydrogen fluoride as shown in the reaction below. Use the change in enthalpy for the reaction above and the bond energies listed in the table below to calculate the average bond enthalpy of the CCl bond, the CCl bonds over here. So again, when you get a table like this with bonds and its energy, you know it's going to be the kind of question where it's going to be the energy of the bonds broken minus the energy of the bonds formed. So let's delve in to this working out. So the energy of the bonds broken in the reaction are always going to be on the left hand side of the arrow, and then the bonds formed are going to be on the right hand side of the arrow. So let's look at the first molecule of bonds being broken, CCl4. So as you can see here, it's got 1, 2, 3, 4 CCl bonds. But we don't know the energy of value of that. That's what we're going to find. So we write an expression something like this. There's 4 CCl bonds, so the expression that we write is 4x. X represents that CCl bond. The next molecule we're dealing with is HF. According to the table, HF has an bond energy of 567. Because there's only one of them, it's just going to stay as 567. So the total energy of bonds broken is going to be 567 from the HF plus the 4x, which is the CCl4. Moving on to working out the energy of the bonds formed, we have these molecules that we're dealing with. So let's do the first molecule. Again, we have CCl bonds, which we don't know the value of. There happens to be 3 of them, so we write the expression as 3x. X represents the CCl. Then we've also got our CF bond over here. The CF bond is with 485 kilojoules per mole. So because there's only one of them, it remains 485. And finally, we've got HCl. We've got one HCl bond, and that's going to be 431. The expression for the total energy of bonds formed is going to be 431 plus the 485 plus the 3x. Okay, so all of that is being plussed together. So the equation we want to plug it into is the bond enthalpy equals energy of the bonds broken minus the energy of the bonds formed over here. Okay, so let's substitute everything that we know in. So the bond enthalpy is given to us already in the reaction up above. So it's negative 21 kilojoules per mole, which is what I've substituted over here. And then for the energy of the bonds broken, I plug in this expression down here, pop it in some brackets so I don't get them mixed up, minus the energy of the bonds formed, the total energy of the bonds formed, which I've gotten from here. Okay, so here's what I have to do. I have to put the like terms together. Let's not forget that the minus which is out of the bracket applies to everything within the bracket. Okay, so what I'm going to do is, first of all, I'm going to condense these values over here, which equals 916, and I've simplified this slightly by doing so. The next thing I'm going to do is I'm going to further simplify this by mixing up my like terms together. So what I did was I did 567 minus, remember this symbol applies to what's in the bracket, 567 minus 916, and that gets me negative 349. And then I've got 4x minus 3x. 4x minus 3x is 1x, which I've written as x over here. Okay, now what I can do is, to get x on its own, I have to do the opposite of negative 349. And the opposite of that is plus 349. So what I do to this side is the same as what I do to the other side of the equal sign. And that cancels things out on this end. And when I simplify it further, I have negative 21 plus 349, which equals 328. So x equals 328. The x, remember, was our unknown bond, which was the CCl bond. So our final answer is to 3 significant figures with units, and that is 328 kilojoules per mole. That is what the CCl bond is worth. That's the energy that is associated with this bond here. Next question. Circle the word in bold below that best describes the polarity of each molecule. As you can see here, I've got a few clues for you. So remember, polar molecules have different atoms around the central atom, and they'll often contain a lone pair as well. It's either of these two or both, okay? So this is the criteria for polar molecules. And then the criteria for non-polar molecules is that it has the same atoms around the central atom and it's got no lone pairs. This is what makes it symmetrical, and because of this symmetry, it allows it to be non-polar as the dipoles cancel out. Okay, but for polar molecules, it's the lack of symmetry which accounts for the dipoles adding up, which creates a molecular dipole and hence a polar molecule. So as we can see here, if we look at Freon, have a think about what this might be based on our 2 criterias. So, does it have different atoms around the central atom? Yes, it does. As you can see here, it's got 3 chlorines and 1 fluorine. Okay, so instantly we know that it's going to be a polar molecule. Doesn't have lone pairs, but because it has different atoms, it is not symmetrical, so it's going to be polar. If we look at carbon tetrachloride over here, it has the same atoms around the central atom carbon. It's got no lone pairs as well, so this makes it very symmetrical. This means that it's non-polar as the dipoles have cancelled out. Okay, there's an equal pull of electrons. When there's an equal pull, those dipoles cancel out. Okay, so based on what we've just learnt, we can be confident that Freon is polar and carbon tetrachloride is non-polar. Okay, so next question. Compare and contrast the factors that influence the polarity of these 2 molecules. Okay, so let's start off with Freon. Down the side, I have a little bit of a prompt. Okay, the first thing that we're going to talk about when we're discussing polarity are the polar bonds. So for Freon, there are 3 polar CCl bonds and 1, that's meant to say and, whoopsies, and 1 polar CF bond around the central atom. Okay, let me just turn off my phone. It's buzzing in the back. 1 polar CF bond around the central atom carbon, with fluorine being the most electronegative. I personally like to add the little dipoles just to show the marker that I know my stuff, okay? And being really specific on what's more electronegative as well. Okay, the next thing I want to talk about is the electronegativity, and that is explaining what electronegativity is in relation to fluorine. So since fluorine is the most electronegative, electrons are more attracted to fluorine than chlorine, which gives it a negative dipole. Okay, remember, electronegativity is an atom's tendency to draw electrons closer to itself. So because fluorine is more electronegative, electrons are going to spend more time around it. making it slightly more negative, which is why it has a negative dipole. So I've explained electronegativity further. The next thing we're going to talk about is shape and symmetry. So Freon has a tetrahedral shape and has no lone pairs. So far, this is what kind of alludes to the fact that it could be symmetrical, but not so fast. However, since there are different atoms around the central atom, the bond dipoles are not arranged symmetrically, okay? So it's not symmetrical. What does this mean? For the dipoles, D for dipoles. As a result, the dipoles do not cancel out, and there is a molecular dipole present. So whenever the dipoles don't cancel out, there is going to be a molecular dipole present. One end is going to be more negative, and the other end is going to be slightly more positive, okay? Because these dipoles do not cancel out. So finally, molecular polarity. Therefore, Freon 11 is a polar molecule. Using the same template, let's talk about carbon tetrachloride. In contrast, because this is a compare and contrast question, let's look at the polar bonds. There are 4 polar CCl bonds around the central atom carbon, with Cl being the most electronegative, as I've shown here. Since Cl is the most electronegative, electrons are more attracted to the Cl, which gives it a negative dipole. Something else I need to mention is, how do you know which one is most negative? Well, we have a rule here. We follow the Fonkel rule. So fluorine, oxygen, nitrogen, and chlorine are the most electronegative in this order. Okay, so that's a super useful thing to remember. Okay, moving on to shape and symmetry. CCl has a tetrahedral shape. It has the same atoms around the central carbon and has no lone pairs of electrons. This means the bond dipoles are all arranged symmetrically, okay? So because of the symmetry, the bond dipoles are arranged in a particular way where the molecular dipole is not existent, okay? The dipoles cancel out, okay? So, last part, as a result, the bond dipoles cancel out and there is no molecular dipole present. Therefore, CCl4 is a non-polar molecule, okay? So, just to rehash about symmetry, a side note, symmetry is dependent on 2 things. It's whether there are the same atoms around the central molecule, or if there are lone pairs or not, lone pair of electrons or not, okay? So that's what the symmetry is dependent on. So by talking about these things over here, you will have a nice full answer for polarity. Okay. Feel free to read back at that in your own time and have a practice of other exam questions that are similar using that structure. Very useful. Anyways, Freon 11 was identified as contributing to the hole in the ozone layer and was banned in 1987. In the uppermost atmosphere, Freon 11 causes the decomposition of ozone, O3. The overall reaction is shown below, where we've got O3 decomposing into O2. This is the energy that is released. We know it's released because it's got a negative sign, it's exothermic. Calculate the amount of energy released when 126 grams of ozone, O3, is decomposed into oxygen gas, okay? So what we're concerned with here is O3. Okay, so what to do? Whenever you are given something in grams, the first step, as I've hinted here, is to turn it from grams to moles, okay? So here we go. Use this equation, N equals mass over molar mass. And so I'm substituting my grams into the mass and then substituting my molar mass of O3, which they've provided down below. Plug that into my calculator, I get 2.625 moles. Okay, so 126 grams is converted to moles, which is 2.625. That's going to come in handy very soon. So the second step, whenever we are asked to find out how much energy is released by this many grams of something, we use this ratio trick. So what I've written here is we have the equation, information that they give us from the actual equation up top, and the ratio for that is the moles to how much energy it releases. And then we've got Q down here, which is the information that they give us from the actual question, okay? And we've got the moles paired up with how much energy it releases. So here's what I've done. As we can see here from the equation, we have 2 moles of O3. Please do not get mixed up between the two oxygens. We're dealing with O3. So we look at O3 in the equation. As you can see, the big number 2 suggests that there are 2 moles of it. How much energy does it release? It releases negative 285 kilojoules per mole, which I've written here. So if 2 moles releases negative 285 kilojoules per mole, how much energy will 2.625 moles of O3 release? Okay, so we've just calculated 2.625 moles, okay, which is equivalent to 1.6 grams. How much energy will this release? So here's what we have to do. We have to find, how do we get from 2 moles to 2.625? What is the common multiplier? To do that, this is what we do. We do 2.625 divided by 2, and then we can find the common multiplier, which will allow us to get from 2 to 2.625. And so that is going to be, if I pop that into my calculator, it is going to be 1.3125. So whatever I do on this side of the equation, I get to do it on the other side of this ratio equation. So the common multiplier, as we just found out, is 1.3125. And so when I am multiplying negative 285 by 1.3125, what am I going to get? Well, I'm going to get negative 374 kilojoules, okay? So I've shown that working out over here. Plug that into your calculator, you will get a bigger number. However, we only want 3 significant figures, okay? So this is how you do it. With a bit more practice, you should be more attuned to it. Just remember 3 significant figures, and a wee note here, we always cancel out the moles per litre and are left with kilojoules, okay? A modern refrigerant compound A, that neither damages the ozone layer nor acts as a greenhouse gas is shown below. Classify compound A as either ionic, molecular, metallic, or covalent network substance. Okay, well, based on the periodic table, these are non-metals, okay? So something that is made up of non-metals is going to be molecular. So compound A is molecular. Refrigerants need to readily evaporate into a gas at room temperature to be effective. Use your knowledge of structure and bonding. Explain why compound A is able to evaporate at room temperature. Okay, so for such a question, this is what we have to do. we have to refer to structure and the bonding. So the bonding is going to be the attractive forces between whatever's making up the structure. So compound A is a molecule held together by weak intermolecular forces between its molecules. Do not say atoms, okay? Because intermolecular forces occur between molecules. So the intermolecular forces will occur between molecules of this, okay? So the reason why it's not atoms is because atoms are bonded covalently and they're actually very strong. So that's not what we're dealing with here. So the next thing that we want to talk about is going to be, what did I say P was for? Okay, well, I'm going to say P was going to be for, I actually don't know. I should have written that down. Oh, P is for properties. My bad. Okay, P is for properties. And so we're linking the structure and bonding to its properties, all right? In this case, the property is that it readily evaporates. So we're explaining why it readily evaporates. Since these forces of attraction are weak, the intermolecular forces, room temperature provides sufficient heat energy to overcome these forces and break the molecule apart. All right. Now, L is for link, so we're linking back to the context. This allows the substance to evaporate readily. Okay, I missed out a little bit there, but add that into your own answer. Alrighty. Alright, we're up to question 3. Let's smash this out. So complete the following table for the substances in their solid state. Freon over here, as you can see, it's made up of non-metals. So the type of solid it's going to be is molecular. The type of particles in molecules are molecules, okay? And the attractive forces between the particles are weak intermolecular forces. Diamond is a giant covalent network or a 3D covalent network. The type of particles it's made out of are atoms. The attractive forces are covalent bonds. Lithium bromide is an ionic solid because it's made out of a metal and a non-metal, okay? The type of particles are cations and anions, and the attractive forces between them are ionic bonding, which is possible due to the electrostatic forces between the cations and the anions. Moving on. Carbon occurs naturally as both graphite and diamond. Graphite readily conducts electricity, while diamond is an electrical insulator. Use your knowledge of structure and bonding to explain the difference in electrical conductivity. All right, so first of all, this question is to do with electrical conductivity. So let's go ahead and explain that first and foremost. So explaining electrical conductivity and what's needed for it. So, in order for a substance to conduct electricity, you should know that there must be free-flowing charged particles, okay? If there are no free-flowing charges, that means electricity cannot be conducted. Okay, so diamond, let's first look at diamond and talk about its electrical conductivity. But before we talk about its electrical conductivity, we need to talk about its structure and the bonding that occurs in it. So which is why this table comes in handy, because we can talk about its structure in more depth, and we can talk about the bonding that occurs between what it's made out of. So diamond is made out of carbons, okay, and it's a 3D covalent network made up of carbon atoms. Don't know why I wrote atoms twice, but that's all right. Atoms held together by covalent bonds. So I've talked about the structure, and I've talked about what it's made up of and the forces or the bonding between what it's made up of. Each carbon, all right, is bonded to 4 other carbons. So carbon only has the max capacity to form 4 bonds, no more than 4. Okay, so all of the carbons in diamond are fully bonded with 4 other carbons. This means that there are no free-flowing valence electrons throughout the structure, okay? Because everything is bonded. There are no lone pairs of electrons flowing around. Therefore, diamond does not conduct electricity, okay? So cool. We've talked about diamond, okay, and how it doesn't conduct electricity. But we do need to compare and contrast and now talk about graphite, okay, and how it readily conducts electricity. Okay, so in comparison, let's talk about the structure of graphite. So, in comparison, graphite is a 2D covalent network. Okay, it's a 2D covalent network made up of layers of carbon atoms. Okay, they're made up of layers of carbon atoms. So these atoms, if you have a look at a diagram, are arranged in hexagonal rings, and they're bonded with strong covalent bonds. Okay, unlike diamond, each carbon is only bonded to 3 others, which means that there's going to be a delocalized valence electron per carbon, okay? There are going to be delocalized valence electrons. Because there are delocalized valence electrons due to there being only 3 bonds, this means that there are free charges able to move around within the structure, within the sheets, in fact, okay? Within the layers of carbons. So that is what allows graphite to conduct electricity, whereas diamond is an electrical insulator. Okay, so solid lithium bromide readily dissolves in water as shown in the equation below. Classify this process as exothermic or endothermic with a reason. Okay, as you can see here, take a minute to have a look at this enthalpy, okay, this delta RH value. Is it positive or negative? It is negative. So, is it going to be exothermic or endothermic? It's going to be exothermic because it is negative. What's the reason? Well, exothermic as the delta RH is negative, which suggests that energy is released to the surroundings, okay? That's why this is an exothermic reaction. The equation for dissolving solid potassium bromide in water is shown below. Both lithium bromide and solid potassium bromide are dissolved in 200 ml of water in separate beakers. So there's 20 grams, let me just do a bit of highlighting, 20 grams of lithium bromide dissolved in the first beaker, resulting in an energy change. Calculate the mass of solid potassium bromide that would need to be dissolved in the second beaker in order to have an energy change of equal magnitude. So we've been given the molar masses, we've been given a mass over here, what to do. We've also got some energy values that we should take into consideration just in case. So I drew out this question because it is a little bit tricky to wrap your head around it. There's a lot going on here. So in one beaker we've got lithium bromide and we've got 20 grams of it. In another beaker we've got potassium bromide, but we don't know the mass of it, okay? So we're going to have to find the mass of potassium bromide. So to find the mass of something, what's an equation that we can use to find the mass of it? Well, an equation that is given to you is N equals mass over molar mass. So let's rearrange it to find mass because that's what we want to find for potassium bromide. So I've rearranged it by multiplying the bottom by big M and doing the same to the other side. And then I've made mass equal to moles times molar mass. And then what we could do is we could plug in what we have. So what is the molar mass? What is the molar mass of KBr? Well, that's given to us over here, so we can plug that in. So I've plugged in 199, which is the molar mass of KBr, but we don't know the moles of KBr, so we cannot work out the mass. So how do we work out the moles of KBr when we're not given much else? Well, let's follow this arrow. As I have mentioned in previous tutorials, another way of working out mass is dividing an energy value by another energy value. Usually it's going to be the energy that is wanted, the energy of concern up top, divided by the energy that's already provided. Okay? In this instance, we have a few bits of information. So the energy of KBr is provided by this equation here. Okay? It's provided by this equation here. So we know that that's going to be on the bottom. Okay? That's what's given to us. But we don't know the energy of lithium bromide. Okay? You might argue that yes, we do. It's up here. It's provided to us. But actually, we don't know the energy provided by 20 grams of lithium bromide. Okay? So that is the energy that is wanted, which is why it's up the top on this fraction. So how are we going to find the energy of lithium bromide? Well, remember, whenever you are given a mass and you want to find the energy, the way we work out the energy given off by a certain mass is by using this little ratio trick. Okay, so we take information from the equation and we are basically comparing it or using it against the information given by the question. Okay, so first of all, when we've been given a mass, we always have to convert it to moles. So how do I convert lithium bromide into moles? We use this equation here, and then we have to plug in 20 grams in the mass value, and then we have to plug in 86.8 in the molar mass, which is from this part of the information. And then we get lithium bromide, 20 grams of it is 0.230 moles. Okay? So now that we've got the conversion from grams to moles, what we can do is we can find out a few things. So we know that from the equation, E for equation, we know that 1 mole of lithium bromide gives off negative 48.8 kilojoules per mole. Okay, and I've written that here. How much will 0.230 moles release? AKA 20 grams. So we've got 0.20 moles down here. How much energy will it release? Okay, well, what I have to do is I have to get from 1 mole to 0.23 mole. I have to find the common multiplier. And that is 0.23. The way I worked that out was 0.23 divided by 1, and that gave me the common multiplier. What I do to this side is what I have to do to the other side. So, negative 48.8 times 0.23, and that gives me 11.2. So, 1 mole releases negative 48 from the equation. In the question, with information that we've been given, 20 grams, which we've converted to 0.230 moles, will give off 11.2 kilojoules per mole. So now, finally, we can plug it into this equation here to find out the moles of KBr to then find out the mass. So there's a lot going on. So we just worked out that 11.2 kilojoules per mole is the energy released by lithium bromide, 20 grams of it. And that divided by 19.9, which was the energy of the KBr given to us in the reaction, is going to be 0.563 moles. So this essentially is what we're able to plug in over here, and then we can work out the mass. So take some time to do that yourself, calculate it, pause the video, blah, blah, blah. And you should get 0.563 times 119 equals 67.0 grams of KBr. Okay. It was a lot, this question. Very, very tricky, which is why it's worth an achieved. Just kidding, it's worth an excellence, of course. So, next question. By considering the enthalpy change of each process, explain any difference in the resultant temperatures of each solution. Okay, so by the sounds of it, we're comparing the temperature differences of these solutions, okay? So what's going to help us figure out the temperature of each solution? Well, we know that temperature is associated with heat, okay? And so we need to figure out how much heat is being given off by each of these reactions or absorbed, okay? So what do we look at? We have to look at the delta RH values of each one. So the dissolving of potassium bromide gives us positive 19.9. Because it's a positive, what does this mean? Is it endothermic or exothermic? It's endothermic, which means that it's absorbing energy from the surroundings. So if it's absorbing energy from the surroundings, what is the temperature of the surroundings going to be? Is it going to be cool or is it going to be hot? It's going to be cool because the heat's being absorbed from the surroundings and into this reaction here because it's endothermic. Comparatively, we've got lithium bromide over here. What is the bonding enthalpy? What is the delta RH, sorry? It is negative. So is it exothermic or endothermic? It is exothermic. So because it's exothermic, it's releasing heat into the surroundings. So what's going to be the temperature of the surroundings? Hotter or cooler? Hotter, because that energy is being released. That heat energy is being released. So going back to our question, with the information that we've got, have a go at writing down or putting into words what we've just explained. Okay, so let's start off with one reaction at a time. So I've started up with lithium bromide. The dissolution of lithium bromide is exothermic, and I've specified that specifically over here, which means that it releases heat to the surroundings. So I've explained what exothermic is. The temperature of this solution will be warm. Okay, moving on to the next solution. The dissolution of KBr is endothermic, and I've specified that here. This means that the reaction absorbs heat from the surroundings. Therefore, the solution will be cool in temperature. Very simple, okay? All right, so next question. Use your knowledge of structure and bonding to explain why solid lithium bromide dissolves in water. Okay, so we have to draw a diagram below. And so how are we going to draw it? We have to draw lithium bromide, which is what is it? What type of solid? Yeah, it's ionic. So, ionic solids are often found in a 3D lattice structure. I wasn't able to draw it, so I wrote about it instead. So it's made out of alternating anions, bromine anions, and lithium cations. Cations are positive because cats have paws, and that's positive. And then anions, I'll let you figure out something that helps you remember that. So anyways, what I've drawn here is water, because we need to show lithium bromide dissolving in water. And so I've shown there to be attractions between the positive dipoles of water, which is the hydrogen, and then the negative regions of our 3D lattice, which is the bromine and anions. Okay, so because of this attraction, we're able to pull this lattice structure apart, as you can see here. And then likewise, the negative dipoles of water, which is the oxygen, is going to be attracted to the positive parts, which are the lithium cations. So that pulls that apart. So these forces of attraction between the water and the anions and cations are strong enough to overcome the forces within this lattice, okay? So overcomes the forces which hold this lattice together and pulls it apart. And that's what I've shown here, okay? So that's something that you should practice. It does seem to pop up in a few exams here and there, so be prepared. So we have to explain this diagram, and we always have to talk about the structure and the bonding between whatever the structure is made up of. So let's do that. Lithium bromide is an ionic solid made up of alternating lithium plus cations and bromine minus anions. So I'm being specific to the context. These are arranged in a 3D lattice structure and are held together by ionic bonds. Okay, so I've talked about the structure and I've talked about the bonding. This is possible due to electrostatic forces of attraction between oppositely charged Br- and Li+ ions. So I've talked about how that bonding is able to occur as well. Now we have to talk about the dissolving process because we need to explain this diagram. What on earth is going on? Well, to reiterate, lithium bromide can dissolve in water as water is a polar solvent. This is because, okay, the O has a negative dipole because it's more electronegative. It is attracted to the lithium plus ions, okay, opposites attract. And the positive dipoles, which are hydrogens, are attracted to the Br- ions, okay. So these forces of attraction between water and the ions in lithium bromide are strong enough to overcome the ionic bonds within lithium bromide, okay? So because of that, this allows the 3D lattice to break apart and therefore allows lithium bromide to dissolve in water. And that is a nice full answer. So remember, whenever we're working through exams together, make sure that you're pausing the video to see if you can answer it and think about it yourselves first. Otherwise, it just becomes a passive experience. And I want to make sure that you are actively learning and challenging yourselves. So all the best for any other practice exams you're doing, and all the best for your exams.